Hello, my name is William Dunn, and this is my Lab 4. Alright, so in this lab we're introduced to the concepts of circuits. Specifically, this lab will focus on introducing resistance, capacitance, current, potential, series, and parallel circuits, though mostly focusing on series, and then RC circuits, which are circuits which have a resistor and a capacitor. So for the series circuit, which is the last version used in the lab, is modeled in a screenshot in the top right corner. You can see the two batteries. Each of those has 1.5 volts. The 47 ohm resistor, and then the 100 ohm resistor. And then we see the ammeter, which reads 0.02 amps, which is my current. The predicted current, which was done by dividing the equivalent resistance and the voltage, gives 0.0204 amps. And then both ammeters read 0.02 amps, so those predictions were accurate. When the connection is reversed, the ammeter reading does not change. When the ammeter is removed and the voltmeter is connected, it reads 3 volts, and the circuit does not move. It reads 0 amps when one of the ammeters is replaced, obviously. This is because the voltmeter does not complete the circuit, because the voltmeter is designed to have a high enough internal resistance that it doesn't affect the circuit at all, so no current will flow through it. The potential differences in various points around the circuit. The potential difference across the batteries was 3 volts. Across this first wire, the potential difference is 0 volts. Across the 47 ohm resistor, the potential difference is negative 0.959 volts. Across the second wire, it's 0. Across the 100 ohm resistor, it is negative 2.041 volts. And then across the last couple wires in the ammeter, there is 0 potential difference. So up here in the top right corner, you can see a graph of potential differences relative to the negative end of the batteries. So from the positive end to the end of that first wire, the potential difference is 3 volts. And then after that first 47 ohm resistor, the potential difference drops to 2.041 volts. Then after that second resistor, it drops to 0. So then my predicted sum of all the potential differences was 0 because of the loop rule. And then the actual sum was 0 because the voltage difference across the batteries ended up equaling out with the potential differences across each of the two resistors. So then the ammeter does not change when the voltmeter is attached to the circuit, because, like I said, the voltmeter is designed to not affect the circuit because it has a high enough internal resistance. The ammeter reading did not change when the voltmeter was connected across the 100 ohm resistor, but when the ammeter was placed in parallel with this resistor, the current increased to 0.06 amps because placing a resistor in parallel will lower the equivalent resistance of the circuit, and also because not all of the current was flowing through that resistor. So then for the 47 ohm resistor, the calculated value using Ohm's law was 47.95 ohms. For the 100 ohm resistor, the calculated value was 102.05 ohms. And then for the wires in the ammeter, the calculated values were 0 because those have 0 internal resistance. Then the RC circuit, which is displayed up here in the top right corner. My observations were that when this current is started, or when this circuit is started with the capacitor initially uncharged, the light starts out very bright in the light bulb and eventually dims and fades out. The same thing happens when the battery is removed and the capacitor is discharged. And then in both situations, the current will start out at its highest value and then decrease to 0 as the charges stop moving. So it took about 4.7 seconds to charge the capacitor with the 10 ohm resistor and 9.8 seconds with the 20 ohm resistor. And then to discharge, it took about 9.5 seconds with the 10 ohm resistor and 18.3 seconds with the 20 ohm resistor. So then this is the graph of the time-dependent voltage discharge. So this is natural log of delta V over delta V naught, which our delta V naught here is 9 volts because that's the EMF. So you can see it's a straight line. The slope is negative 0.1667, which is equal from our equation to negative 1 over RC. So when you solve for the RC value from the slope, you get 5.9998, and then the calculated RC value is 6. So this graph is an accurate depiction, and that slope is accurate. And then the conclusion questions. So if I'd been doing this lab with a real circuit and used a real ammeter, it would have very, very slightly altered the experiment by slightly decreasing the current, because the idealized ammeter on the software has zero internal resistance, but a real ammeter in real life has to have some non-zero internal resistance. And then if we used a real battery to charge a real capacitor in a circuit that did not have a resistor, so if it was just a battery and a capacitor, the process would be an almost instantaneous one. In the computer simulated model, if you connect the circuit and then click play, it does instantaneously charge the capacitor, but that's because the idealized wires and the battery within the circuit software have zero internal resistance, whereas in real life there would be some non-zero internal resistance, but the process would still be extremely quick, because there are no major resistors to impede the charges building up on the capacitor plate. This concludes my lab 4. Thank you very much.